Everyone. Okay, so today we are going to be looking at action potentials of cardiac muscle cells. Okay, just as skeletal muscles and nerve cells, cardiac muscles also undergo action potential. So when you talk about action potential of cardiac muscle cells, it refers to the electrical charges that occur across the membrane of the heart muscle cells. Okay, so this happens during one heartbeat. So you find that these electrical events allow the heart to contract and pump blood effectively. So it is important for us to get to know how this action potential comes into play. Okay, so cardiac muscle action potentials, you find that they are longer as compared to the skeletal muscle or the nerve cells. Okay, so this is mostly due to calcium that comes into play in terms of the action potentials of cardiac muscles. Okay, so you find that calcium plays a major role, a big role in this action potential. No wonder the action potential duration is longer than normal. Okay, so you find that it occurs in 5 phases. Phases from 0 ranging to 4. Okay, so we're going to try and look at the phases of the action potential of these contractile muscles. So the first phase being the resting membrane potential phase, which is phase 4. Okay, so for phase 4, it is the resting phase. So you find at this stage, the cell retains to its resting membrane potential of negative 90 millivolts. Okay, so this one is maintained by the sodium potassium pump and potassium leaking channels. Okay, so this will result in a cell being ready for a next heartbeat. So the resting membrane potential is the first phase of this action potential of contractile muscles. Okay, then we go to the 0 phase. So for the 0 phase, it is known as the depolarization phase or the rapid depolarization phase. So this is due to gap junctions or conduction fiber actions. Okay, so in this phase, you find that the voltage-gated sodium channels open. So for positive sodium ions, you find that they start going into the cell. Okay, so they start going into the cell. So this brings the cell into a state of depolarization because of the sodium that is rapidly entering the cells. So you find that the membrane potential becomes more positive. So from about negative 90, it starts heading to positive 20 millivolts. Okay, so this results in a sudden rise in the action potential. So if you can see our diagram here, it is showing at phase 4, the cell is at rest. You can see at phase 4, the cell is at rest here. And then we have the 0 phase where it's showing this straight line. So at this phase, you find that the 0 phase, there is sodium influx into the cell. Okay, so using these sodium channels. Okay, and then it reaches a peak at after it surpasses this 20 millivolts, it reaches its peak somewhere here. So when it reaches its peak, it now enters the temporally repolarization phase. So for the temporal repolarization phase, it is when the potassium channels open up. So when these potassium channels open up, they allow some potassium to go outside the cell. Okay, so you find that the sodium channels, they'll close, and then potassium, it briefly leaves the cell through the transient potassium channels and slightly drop in, there'll be a slight drop in the membrane potential. Okay, so this is in phase 1. So it is characterized by potassium. Then after that, you can see on this graph that there is this plateau that it forms. So this plateau that it forms is known as the plateau phase, which is phase 2. So phase 2 is a plateau phase. So what happens in here is that there will be voltage gated calcium channels that will fully open. Okay, so when they are fully open, this starts the initial depolarization again. So for calcium channels, they open up and calcium starts going into the cell. Okay, so this phase is unique to the cardiac muscle as compared to the skeletal muscles and the nerve cells. Okay, so you find that at the same time, potassium leaves the cell and calcium enters the cell through the slow L-type calcium channels. Okay, so because calcium entry balances the potassium exit, you find that the membrane potential, it will stay almost constant. That's why it forms this plateau in this graph. So you find that this is important as it allows long contraction of the heart muscles, and it also prevents a continuous contraction of the heart. Okay, so this phase is important and it is unique to the cardiac muscles. Then we have the third stage or third phase, which is phase 3. So in phase 3, it is known as the repolarization phase. So in the repolarization phase, you find that the calcium channels, they'll close. Okay, they'll close, and then potassium permeability increases. So when it increases, you find that potassium leaves the cell rapidly through the potassium channels. Okay, so this causes a quick repolarization due to this potassium leaving the cell. Okay, so you find that the membrane potential will return towards the negative 90 millivolts. Okay, it will start returning back to its resting membrane potential. So this is generally how an action potential occurs for a cardiac muscle cell to contract, okay, to generate that action potential and contract. And this is what helps the heart to conduct its function. I hope this video was helpful, and if you want to get to listen or learn more about such topics, you can just subscribe to our channels, to the drive, so that you can access more of such videos. Okay, thank you for watching our video.